As examples of this division of apparent power into solely real or solely reactive components, consider a resistor experiencing 200 volt amperes of apparent power at an angle of 0 degrees, 200 watts of which is being dissipated as real power since none of it is being directed towards a reactive interchange. In this case, the apparent power vector perfectly overlaps the real power component. Similarly, consider an inductor experiencing 40 volt amperes of apparent power at an angle of positive 90 degrees, 0 watts of which is being dissipated as real power since positive 40 volt amperes of it is being directed towards a reactive interchange. Although I personally loathe this terminology, you might hear people saying that this inductor is absorbing 40 VARs of reactive power. In this case, the apparent power vector perfectly overlaps the positive reactive power component. Finally, consider a capacitor experiencing 25 volt amperes of apparent power at an angle of negative 90 degrees, 0 watts of which is being dissipated as real power, since negative 25 VARs is being directed towards a reactive interchange. Again, I personally loathe this terminology, but you might hear people saying that this capacitor is supplying 25 VARs of reactive power. In this case, the apparent power vector perfectly overlaps the negative reactive power component, where the negative 90 degree angle accounts for polarity. Moving on. You'll note this first batch of AC power example problems use voltage as the reference from which current is measured. While referencing current with respect to voltage is a commonly accepted practice and an absolute necessity for AC power calculations, this isn't always the case. As such, let's step this up a notch and try some example problems including scenarios in which some other outside absolute reference is employed. Given the following information, solve for the desired properties. As previously, you'll note voltage and current have already been expressed as phasor equivalents, and any complex impedances have already been calculated. Express all answers using proper engineering units. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For our first example problem, we've been given a voltage phasor equivalent of 86 volts at an angle of positive 17 degrees, and a current phasor equivalent of 80 milliamperes at an angle of positive 35 degrees, and are being asked to solve for the resultant apparent, real, and reactive power. Despite employing some absolute external reference, there appears to be a 35 minus 17 or 18 degree relative phase shift between voltage and current can be said to lead voltage by a relative 18 degrees. Don't make relative phase shift a big deal. Just look at the phasor diagram. When expressed using voltage as the reference, the voltage phasor equivalent is 86 volts at an angle of 0 degrees, and the current phasor equivalent is 80 milliamperes at an angle of positive 18 degrees. This is the format we require for apparent power calculations, and anything else simply will not work. Given current appears to lead voltage, we're most likely dealing with a slightly capacitive impedance, and as such, we should expect our resultant real power to be less than our apparent power magnitude and our reactive power to be negative. Let's see if this is the case. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we find apparent power to be roughly 6.9 volt amperes at an angle of negative 18 degrees. When resolved into its real and reactive components, we find real power to be roughly 6.5 watts and reactive power to be roughly negative 2.1 volt amperes reactive. As expected, real power is less than apparent power magnitude and reactive power is negative given the slightly capacitive nature of the impedance in that current leads voltage. For our second example problem, we've been given a voltage of 120 volts at an angle of positive 22 degrees and a current of 800 milliamperes also at an angle of positive 22 degrees. We're being asked to solve for the resultant apparent, real, and reactive power. Note both voltage and current have the same phase shift of positive 22 degrees. This implies voltage and current are perfectly in phase with one another. There is a 0 degree relative phase shift between them. When expressed using voltage as the reference, the voltage phasor equivalent is 120 volts at an angle of 0 degrees, and the current phasor equivalent is 800 milliamperes at an angle of 0 degrees. Given current appears to be perfectly in phase with voltage, we're most likely dealing with a purely resistive impedance, and as such, we should expect all of apparent power to be directed towards real power, and none of it towards a reactive interchange. Let's see if this is the case. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we find our apparent power to be 96 volt amperes at an angle of 0 degrees. When apparent power is resolved into its real and reactive components, we find real power to be 96 watts and reactive power to be 0 bars. As expected for this purely resistive element, all of apparent power is being directed towards real power and none of it towards a reactive interchange. As we previously discussed, the apparent power vector perfectly overlaps the real power component. For our third example problem, we've been given a voltage of 105 volts at an angle of negative 14 degrees and an impedance of 280 ohms at an angle of positive 40 degrees, and are being asked to solve the resultant apparent, real, and reactive power. Given the impedance appears to be somewhat inductive because of the positive impedance angle, we should expect our resultant real power to be less than our apparent power magnitude and our reactive power polarity to be positive. Let's see if this is the case. We could use Ohm's law to solve the current. However, we can use an alternate version of the AC power formula. Apparent power is the complex conjugate of voltage squared divided by impedance. When voltage is employed as the reference as required, the voltage phasor equivalent is 105 volts at an angle of 0 degrees. Substituting in our given values, we find apparent power to be 39.4 volt amperes at an angle of positive 40 degrees. When apparent power is resolved into its real and reactive components, we find real power to be 30.2 watts and reactive power to be positive 25.3 bars. As expected, real power is less than apparent power and reactive power is positive given the somewhat inductive nature of the impedance. Given this inductive nature, we might expect current to lag voltage by a relative 40 degrees. A simple manipulation of the power equation, or just as easily Ohm's law, supports this hypothesis. Solving for current and substituting in our given values, we find current to be 375 milliamperes at an angle of negative 40 degrees using either method. Keep in mind, this calculated phase shift is only relative in nature. If we employ the previously agreed upon absolute reference, such that voltage is 105 volts at an angle of negative 14 degrees, current using this same reference would be 375 milliamperes at an angle of negative 54 degrees. Again, don't make relative phase shift such a big deal. Just look at the phasor diagram. Regardless of the reference employed, current can still be said to lag voltage by a relative 40 degrees. Alright, let's end this lecture with a couple quick scenarios examining the practical applications of AC power calculations. First, let's consider an industrial AC motor. Ordinarily, most industrial motors run off three-phase AC. However, let's concern ourselves solely with a single winding. We'll examine the details of three-phase AC and industrial three-phase AC motors in later lectures. Let's say the single winding experiences a voltage differential of 120 volts, and while the motor is unloaded, the single winding draws, let's say, 507 milliamperes of current at a power factor of 0.17. An example of an unloaded motor would be a free-spinning grinder before the grinder makes contact with a workpiece, where rotational speed is pretty high. However, the twisting force or torque produced by the rotating shaft is relatively low. If, however, the motor is loaded, let's say the grinder actually makes contact with a workpiece and the twisting force or torque produced by the rotating shaft is relatively high, the motor winding draws 994 milliamperes of current at a power factor of 0.84. It should be noted that motor windings, note the dramatic emphasis of the term winding, are primarily inductive in nature. Although it's not ordinarily explicitly mentioned, it is assumed that all motors are always inductive in nature, and you can always anticipate current to lag voltage. See if you can determine the apparent, real, and reactive power consumed by this motor winding in both the unloaded and the loaded condition, and then compare the two conditions. You should notice something very interesting in this comparison. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Long story short, when the motor is unloaded and just free spinning, not a lot of real work is being done. This is evident by the piss poor power factor of 0.17. Really, the only thing the 507 milliamperes of current drawn from the power supply in the unloaded condition is doing is establishing a magnetic field and maybe accounting for a tiny amount of real power lost due to heat or friction. In the loaded condition, however, a substantial amount of work is being done, evident by the much larger power factor of 0.84. However, the motor still requires a magnetic field to operate. Thus, we'd still expect a portion of power to be directed towards a reactive interchange. Let's examine the unloaded condition first. Apparent power magnitude is voltage times current. Substituting our given values, we find apparent power magnitude to be roughly 60.8 volt amperes. This really illustrates the origin of the term apparent power. If we were unaware of phase shift between voltage and current, relied solely on the effective value of voltage and current, we'd be under the false impression that this motor was apparently consuming 60.8 watts of real power. The reality is far, far from the truth. Real power is apparent power magnitude times power factor. In the unloaded condition, an extremely lame 0.17. Substituting in our given values yields a real power consumption of only 10.3 watts. This is the small amount of real power accounting for frictional heat losses when the unopposed motor is just free spinning and not doing any actual work. As we anticipated, real power in the unloaded condition is relatively small, meaning only a small portion of power the motor is apparently consuming is being directed towards actual work, and a vast majority of it will be directed towards a reactive interchange characteristic of primarily inductive elements like motor windings. Let's solve for reactive power using one of our previously derived methods. Reactive power Q equals the square root of the differences of the squares of apparent power S and real power P. Substituting our given values yields a reactive power of roughly 60 volt amperes. Given we know current to lag voltage, we're certain the sign of reactive power is positive. As we anticipated in the unloaded condition, a large majority of the power the motor is apparently consuming is being directed towards the reactive interchange and very little of it towards actual work. Granted, we solve for these quantities without using angles or complex numbers. However, we could assemble apparent power as a complex number in rectangular format as 10.3 plus J 60, and then convert it into polar format as 60.8 volt amperes at an angle of positive 80.2 degrees. Again, I find these plots extremely gratifying as they clearly illustrate the spatial relationship of apparent, real, and reactive power. Let's now examine the apparent, real, and reactive power for the loaded condition using the alternate technique, notably by employing complex numbers and angles. If you wanted to, you could use the same techniques as we did in the unloaded condition, but let's try something new for the sake of variety. As previously, apparent power magnitude is voltage times current. Substituting in our given values, we find apparent power magnitude to be 119.3 volt amperes. Compared to the unloaded condition, we're apparently consuming more power. This should be expected given the grinder is making sparks fly. Where, however, is all that apparent power being directed? Real or reactive? To answer this question using complex numbers, we can solve for the apparent power angle by taking the inverse cosine of power factor. Substituting in our given values yields an angle of roughly 32.9 degrees. Note the apparent power angle is assumed to be positive since we're obviously dealing with an inductive impedance because current lags voltage. Apparent power, expressed as a complex number in polar format, is therefore 119.3 volt amperes at an angle of positive 32.9 degrees. Thus far, we've been resolving apparent power into its real and reactive components the hard way. Let's use our scientific calculator to perform this task in a far more efficient manner by converting this polar number to one making use of a rectangular format. Doing so yields 100.2 plus J 64.7. The real horizontal x component is real power. Real power is roughly 100.2 watts. The imaginary vertical y component is reactive power. Reactive power is roughly 64.7 VARs. As we anticipated, real power in the loaded condition is much larger, almost 10 times larger than the unloaded condition, meaning a larger proportion of apparent power is now being directed towards actual work. Note, however, the motor still consumes a measurable amount of reactive power in the loaded condition. In fact, despite a dramatic increase in real power consumption, the reactive power consumption remained relatively constant, only increasing ever so slightly. This is a classic characteristic of induction motors. A plot of real and reactive power input on the vertical axis as a function of mechanical power output on the horizontal axis illustrates this behavior quite succinctly. As mechanical power requirement, i.e. doing real labor, increases, the reactive power requirement remains relatively constant for the entire range, whereas real power consumption almost linearly increases. This is to imply that induction motors consume real power roughly linearly proportional to the applied load, but at all times must consume a relatively constant amount of reactive power simply to keep the motor spinning. We'll examine this feature and much more about induction motors in later lectures. Alright, one more illustrated example problem before I cut you loose, this time featuring a transformer. A transformer is an electrical device that, in summary, steps up or steps down applied voltage. We'll examine the inner workings of transformers in later lectures, but let's dispel a common misconception about transformers using our newfound knowledge of AC power calculation. Since transformers contain no moving parts, a common assumption is that they are nearly 100% efficient. This isn't really true, as we'll soon demonstrate. Consider a transformer modeled as a black box, where incoming voltage and current of a specific magnitude is transformed, hence the name, into voltage and current of another magnitude. If a transformer was truly 100% efficient, power input should equal power output. Let's see if this is the case. Consider a transformer being supplied 120 volts AC from a residential outlet. The transformer is being used to step down the supply voltage to 24 volts AC to power some consumer electronics device, either a lamp, a computer, a battery charger, or something else that necessitates a smaller operating voltage. Let's say the device in question is modeled as a purely resistive load of 5 ohms. An ammeter at the output of the transformer indicates the device draws 4 amps of current. Let's calculate the apparent power output of the transformer. The apparent power output of the transformer is the complex conjugate of the voltage times the current. Given this is a purely resistive load, there will be no phase shift between voltage and current, and all of apparent power will be directed towards real power and none of it towards a reactive interchange. Substituting in our given values and solving for the real and reactive components, we find this to be the truth. Of the 115.2 volt amperes at an angle of 0 being output by the transformer, all of it is being directed towards 115.2 watts of real power, and none of it is being directed towards a reactive interchange. Here's where our earlier assumption might prove false. If a transformer was truly 100% efficient, what's the power input to the transformer, and what is the current drawn from the 120 volt source? By all means, pause the lecture and think about this. If you're tracking, you should have come up with the following results. If the transformer was truly 100% efficient, power in should equal power out. Given power output has been calculated to be 115.2 volt amperes at an angle of 0 degrees, one might expect power input for a 100% efficient device to be also 115.2 volt amperes at an angle of 0 degrees. Let's now solve for the current drawn from the residential supply. Apparent power to the input transformer is the complex conjugate of the voltage times the current. Solving for current and substituting in our given values, again assuming there to be no phase shift between voltage and current given the purely resistive load at the output, we find current to be 960 milliamperes at an angle of 0 degrees. In summary, power in equals power out, not only in magnitude, but also flavor. Note in the idealized 100% efficient scenario, power input has the same characteristics of power output, and that all of it is real and none of it reactive. Again, this hypothetical scenario is what we'd expect of a perfectly 100% efficient transformer. Power in equals power out. No change in flavor. Let's now examine a non-ideal transformer and see if it matches these lofty expectations. As previously, an ammeter on the output indicates our 5 ohm resistive load draws exactly 4.8 amps, perfectly in phase with the 24 volt AC output of the transformer. As previously, the power output of the transformer is 115.2 volt amperes, all of which is being directed towards 115.2 watts of real power and none of it towards a reactive interchange. This time, our non-ideal transformer is observed to draw not 960 milliamperes as previously, but rather 1 amp from the 120 volt AC residential supply. Additionally, this current appears to slightly lag supply voltage by, let's say, 7 degrees. Current therefore can be represented using a phasor equivalent as 1 amp at an angle of -7 degrees. Given we've observed a slightly higher current draw and slight phase shift between voltage and current than the ideal scenario, we might expect a tiny portion of apparent power to be directed towards a reactive power interchange. What is the power input to this non-ideal transformer, and is all of it being put to good use? By all means, pause the lecture and think about this. If you're tracking, you should have come up with the following results. Apparent power input to the transformer is the complex conjugate of the voltage times the current. Substituting our given values and solving for the real and reactive components, we find our expectations to be true. The non-ideal transformer seems to be consuming 120 volt amperes of apparent power, of which 119.1 watts is being directed towards real power and 14.6 volt amperes reactive is being directed towards a reactive interchange. How efficient is this transformer? Think about it. 115.2 watts of real power is being put to actual use. How much real power is it drawing from the source? You might rush to the assumption it's consuming 120 volts times 1 amps of power, but this is incorrect. We demonstrated that the transformer is in actuality consuming 119 watts of real power, of which 115.2 watts is passed on to be put to beneficial use. Only a measly 3.6 watts is considered a loss. In this case, the transformer is not 100%, but rather 115.2 over 119.1, or 96.6% efficient. 96.6% in my estimation is close enough to consider this device relatively ideal. Hold on, wait a minute, some of you may say. Where did that extra 14.6 VARs go? Why isn't this transformer actually 115.2 over 120, or 96% efficient? Here's the reason why. Long story short, the 14.6 VARs went nowhere, but rather it was regularly consumed and returned or exchanged with the power supply and didn't actually contribute to the actual real power transfer of the transformer. The reactive power interchange solely went to the establishment of the magnetic field necessary for the proper operation of the transformer, as did the reactive power consumed by the motor. Really, efficiency only affects the proportion of real power transfer between devices or stages of a larger electrical system, and not the transfer of apparent power. As an additional example of efficiency, let's return to our previous motor example. Recall that the loaded motor consumed 119.3 volt amperes of apparent power at an angle of positive 32.9 degrees, or a power factor of 0.84. This means the motor consumed 100.2 watts of real power and 64.7 volt amperes of reactive power. Let's say, however, the motor did only 86 watts of actual mechanical work, and 14.2 watts was lost to heat, friction, and/or noise. In this scenario, the motor would be 86 over 100.2, or roughly 85.8% efficient. This is where I like to think of power factor and efficiency both as hoops through which input apparent power has to jump one after another to yield usable output real power. If apparent power is to be considered a theoretical maximum in which there is no phase shift between voltage and current, and all power is assumed to be positive, power factor is the first hoop through which apparent power must jump to yield real electrical power delivered to that device. Reactive power, while an important dimension of apparent power and undoubtedly essential to the operation of devices like motors and transformers, both of which require magnetic fields to operate, is excluded from consideration by this first power factor hoop. Efficiency, the second hoop, shaves off all real power losses like heat, friction, and/or noise from real electrical power input and yields real power output. Again, old-school power calculation methods are extremely barbaric, but extremely effective. Consider a device that consumes 1 kilovolt ampere of apparent power, has a power factor of 0.9 and efficiency of 95%. Jumping through the power factor hoop, the input real electrical power is 900 watts. The 435.9 VARs of reactive power, while essential to the device's operation, is excluded from consideration. When real power jumps through the efficiency hoop, it yields 855 watts of usable power output, where 45 watts have been lost to heat, friction, and/or noise. Let's come at this from yet another direction. Consider a motor nameplate that explicitly states the motor produces 400 watts of real mechanical power output and has a 0.87 power factor and is 92% efficient. This means for the motor to yield the desired 400 watts of output mechanical power, it necessitates at least 400 over 0.92 or 434.8 watts of real electrical input, of which 34.8 watts is lost due to inefficiencies. This additionally means that this motor must consume 434.8 over 0.87 or roughly 499.8 volt amperes of apparent power. The 246.4 VARs of reactive power, while essential to this motor's operation, is excluded from consideration by power factor. Is power factor synonymous with efficiency? No, it is not. Apparent power is composed of two dimensions, real and reactive, both of which are necessary for the proper operation of an electrical device. Power factor merely removes the reactive portion from consideration for the purposes of efficiency calculations. Alright, that about concludes this series of illustrated examples. In conclusion, this lecture examined applications of AC power calculations by way of a series of illustrated example problems. If your self-assessment indicates you are so qualified to move on, by all means, do so. If, however, you struggle with these example problems, I recommend you revisit and review this material, since AC power calculation will become an important technique in remaining AC circuit analysis scenarios. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.